What's up, guys? So we're talking about Pascal's triangle, and Pascal's triangle has a lot of applications, and we are barely going to scratch the surface of those applications. But for Algebra 2, the main reason we're going to use it is for binomial expansion, which I'll get to in a minute. But first of all, let's talk about what is Pascal's triangle. Now, I have it here for you, and you can see how it goes out to row 10, which is actually the 11th row, if you'll notice, because it starts at 0. But you can easily draw this yourself. I know you're thinking, there's no way I'm going to be able to remember these numbers. Well, I don't know most of these rows either. But I can tell you it's very easy to make. So what you do is you can just do this on your own paper. You can start with a 1, okay? And then just remember that every row begins and ends with a 1. So I'm going to say 1, and then I'm going to say 1, 1. And then I'm going to come down here and notice that it's getting 1 larger every time. And so I'm going to start with 1. And now each number is going to be the sum of the two numbers above it. So 1 plus 1 makes 2, and then end in a 1. Now I'm going to come down here and put a 1. And then 1 plus 2 makes 3. 2 plus 1 makes 3. And then end with a 1. Start with a 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And then end with a 1. And you can do this on and on and on, and it always works. So let's check this number 56, for example. That is 21 plus 35. So because you have this rule, you can actually draw this thing out as far as you want to go. I could do the next row for this one. So row 11, I could say 1 plus 10 would be 11. Started with a 1, of course. 10 plus 45 is 55. 45 plus 120, that'd be 165, and so on. And you could actually continue this out as far as you want to go. So that's what Pascal's triangle is in a nutshell. Now, how it's used is a very long subject. There's a lot of uses for Pascal's triangle, as I said. So binomial expansion. Binomial expansion is when you take a binomial, that's two numbers that are being added or subtracted, right? And if they are raised to a power. Now, we've already in class done some binomials squared. We've even done some binomials to the third and fourth power, but we actually multiplied those out by hand. What happens if I ask you to do a binomial to a much higher power, say 8th or 9th or 10th power? You could multiply them one by one and get a really, really long polynomial answer. But there's a faster way to do it using Pascal's triangle, and that's what we're going to talk about here. So as it turns out, this pattern, which looks kind of complicated, but it's really not, is the polynomial that you would get when you raise a binomial to the nth power. So let's just say the first term of the binomial is a, the second term is b, and they could be anything. It doesn't really matter. The power that we raise them to, we're going to call that n. What's going to happen is, where these little hashtags are, these numbers are going to correspond to a row in Pascal's triangle. And that row is going to be whatever row corresponds to n. So for example, if we raise something to the 5th power, or let's look at this example. So for example, if we raise something to the 3rd power, then that's going to be the same as the 3rd row of Pascal's triangle. Now I know you're looking at this saying, wait a minute, I see that looks like the 4th row to me. Well, remember, rows always start with the 0. So this is the 0 row, the 1st, 2nd, 3rd row. And when we count the terms, that's also going to start. This is the 0 term, and then 1, 2, 3rd term. Okay, so keep that in mind. The rows and the number of rows and the number of terms in a row, we label them starting with 0. So if I want to do a plus b to the 3rd power, then that means I'm going to go down to the 0, 1, 2, 3rd row. Okay, 1, 3, 3, 1 is going to correspond to the coefficients of these terms, terms of the polynomial. 1, 3, 3, 1. Now, what about this other stuff? A to the 3rd, b to the 0, a to the 2nd, b to the, what would that number be? 1. A to the 1st, b squared, a to the 0, b to the 3rd. So what's going on here? Do you see a pattern? As it turns out, this pattern is the pattern that it's always going to use. So a is going to start out at the nth power. We raised a plus b to the 3rd, so our first term is going to have a to the 3rd. These numbers are going to be the same. B will start at 0. Now a is going to go down by 1 each term until it gets to 0, while b is going to count up by 1 each term until it gets to 3. And that's actually what this is saying here. This is saying A will start at the nth power, B will start at 0, and then you're going to do A to the n minus 1, meaning it's going to go down 1. A to the n minus 2, meaning it's going to go down 2, and so on. B is going to start at 0, and then 1, and then 2. Dot, dot, dot means it's going to continue in this way until you get to where A is raised to the 0 power, and B is raised to the nth power. So, looks complicated, but again, if you follow this pattern, it's really not too bad. So, if A was raised to a different power, whatever power that is, then the pattern would continue this way. You would find that row of Pascal's triangle and then label the coefficients with those numbers, 1, 3, 3, 1 in this case, and then start A at that power and go down by 1 as you continue. So in this case, once we simplify this, meaning, get rid of B to the 0 is 1 and things like that, this is what it's going to look like. Okay, so here's another example. We're going to expand A plus B to the 5th power. Now, if you look at Pascal's triangle, and I'm going to go back here, if we go to the 5th row, 0, 1, 2, 3, 4, 5, remember to start at 0. The 5th row says 1, 5, 10, 10, 5, 1. These numbers, okay? That means the expansion at the beginning of each term is going to be 1, 5, 10, 10, 5, 1. And A and B, A is going to start at the 5th power because it was raised to the 5th power, and it's going to go down by 1 each time. B will start at 0 and go up by 1 each time until it gets to 5. Again, simplifying this, B to the 0 is 1, so it goes away in this term. That's really about the only thing over here. A to the 0 goes away, so there's no A. We don't need to write our 1 coefficients, things like that we know at this point, and that's how it simplifies. Okay, so what happens if instead of A and B, we actually have some stuff there? So that's the next example. So this is saying, let's call A 2x, and B is 3y. So it's actually got a number and it's got a letter. So it's actually a little more complicated. Well, we're still going to do the exact same thing. In this case, it's the 4th power. So if we go to the 4th row of Pascal's triangle, this is what you get. 1, 4, 6, 4, 1. Let's check. 0, 1, 2, 3, 4. Right here, 1, 4, 6, 4, 1. Okay, so those are the coefficients of our terms. What are the terms? Well, here's what we're going to do. This whole term, 2x, is A. The whole 3y term is B. So anywhere that I would normally put an A, like up here, anywhere I would normally put an A, I'm going to put parentheses, and inside that, I'm going to put whatever A is, which is 2x. And inside these parentheses, I'll put in whatever B is, which is 3y. And it's exactly the same as what we did before. I'm just substituting for A and B with what A and B are. Okay, so now we have to simplify this. And this is where it gets a little bit harder than what we had before, although it's still not that bad. It's just a little bit of extra work because we're not just going to say A to the 4th anymore. We've got to actually figure out what is 2x to the 4th, and that takes a little bit more work. So 2x to the 4th, well, 2 to the 4th is 16, and x is to the 4th, so that's going to give us 16x to the 4th. And 3y to the 0, well, anything to the 0 power is 1, so we don't really need to write that. Now the next term, you've got 4 times 2x to the 3rd times 3y to the 1st. The 4, which is going to be 4, 2x to the 3rd, okay, 2 to the 3rd is 8, and x to the 3rd, so that's giving us this. 3y to the 1st, that's 3y. The next term, 2x squared, that's going to be 2 squared, which is 4, and x squared, which is x squared. Again, the 6 came down. And 3y squared is 9y squared. Now we have 4, 2x to the 1st, which is itself, 3y to the 3rd. Well, 3 to the 3rd is 27, so we get 27y to the 3rd. And finally, 2x to the 0 is 1, so that part of the term goes away. And 3y to the 4th, 3 to the 4th is 81. Now we have to do one more step of simplifying, kind of multiplying each term out. So 16x to the 4th, it's already done. 4 times 8 times 3, that's 96. And you're going to have x third y. 6 times 4 times 9, that's 216. 4 times 2 times 27, also 216. And then 81. Notice that the variables simply kept their powers, like so. And that's it. That's how we're going to use Pascal's triangle to do binomial expansions.